homework over the weekend if you guys have chapter 5 problems. Delaney? Number 8. Okay. So I don't mean to like pick on you or to like make it awkward or anything, but I think it'd be most productive if you kind of help me out with what your ideas were so we can get you some more individual feedback on these problems, because there's not really like one way you have to do them.
Okay. Why is it close and then the case square crossed out so then it's can and then the parentheses can over.
So you just did this. Great. Right? So the next thing you'd want to do is figure out a way to get rid of that.
Okay.
So if you notice, that's one of the cotangent identities, or I'm sorry, cofunction identities, because that's just equal to cotangent. Is that okay?
Why did you decide to cotangent and why did you figure out?
So if I go back and I look at my identity sheet, the only stuff that has a pi over 2 minus is these guys in here.
Okay.
And I notice that this is exactly what I have, right? Tangent of. I just made it equal to cotangent. Cool.
I was just a little confused. But now I understand.
This is why I wanted to, like start doing it the same way you were going to do it. Okay. What would we want to do next? We still have a little bit more to do here. Dan? Okay. We still have to finish this though. We're not done. That's okay. 14 is next, but that's okay. No problem. You misunderstood. It's not the end of the world. You guys can lay off. What might we want to do next on this? Jessica.
Well, cotangent is really cosine over sine, and the cosine is really over sine.
Great.
So I wrote that out, and then
Yeah, so let's
sorry.
yeah, nope, I love where your head's at. You're telling me lots of good things. It's just going a little bit fast. So let's think about it that way. Everybody's okay with that? And I think doing this is going to make it a little less fractiony for everybody. So you said cotangent is the same thing as cosine over sine. And in general, if you're not sure what to do, right, rewriting everything in terms of sine and cosine is usually a good idea. So if you get to a point, it's like, boy, I don't know what to do. If everything's not already sines and cosines, find a way to do that. Now, 1 over cosecant is the same thing as just sine. That was one of our reciprocal identities. And because it's being multiplied to a fraction, I wrote it as like sine over 1. And then, whoop, whoop. And we're left with cosine. And you can't do better than one identity, right? So that's as good as we can do. Delaney, are you okay with that?
Yeah, that makes a lot more sense.
Okay. Dan, you wanted to do 14? Sure, no problem. Okay. What did you try to do first? Did you come up with anything?
Yeah. Oh, I deleted it.
That's okay. If you press Control Z, it'll undelete the last thing you deleted. Or is it an old delete? I mean, if it's not just I did it a second ago, it's probably not going to do anything. Okay. Then don't worry about it. That won't do nothing. Okay. So do you see any identity thing that's obvious to use here? I have a 1 minus sine y and a 1 plus sine y. So that would need 1 minus sine squared
Yeah.
that we don't have. But we could make that, right? What could I multiply the top and bottom of that fraction to make 1 minus sine squared?
Multiplied by negative sine.
How about 1 plus sine squared? Why would that work? Yeah, it's a difference of 2 squares now, right? Can I see that? And let's do the same thing for this one then. So if you don't see that right away, this would be the same idea as like just making a common denominator, right? That's the other thing you could have thought of. It's just, oh, I'll make a common denominator as well. So when I do that, the numerator, 1 plus sine y plus 1 minus sine y. And if I FOIL out that denominator, that's 1 minus sine squared y. If we combine like terms in the numerator, what's going to happen? Those guys cancel too. We okay there? In the denominator, we know cosine squared is equal to 1, right? If I subtract sine squared from both sides, I get that cosine squared is equal to 1 minus sine, right? 1 plus 1. No problem. It is a bendy one. So I can just rewrite 1 minus sine squared y as cosine squared. Hi. Sure. That's fine. Thanks, Caroline. Is that, it's not your name, you're Anna. Dang it. No, I can't even win most of them, though. It's too late in the year to be doing this, Mr. Kulik. Blaming the masks has gotten old. You just don't know me. It's like, it is really hard. Anyways, everybody okay so far? Dan, are you okay? Say no if you're not. Okay, where did I lose you? Okay, that's just me justifying changing 1 minus sine squared into cosine squared. So the way I did that is I started with the Pythagorean identity, and I subtracted sine from both sides, or sine squared from both sides to make this new identity. And that's how I justified doing that switch up above. Is that okay? And I can do a little bit better than this, what I have at the end. Since it's a fraction, I can write this as not a fraction. So notice that this would be the same thing as 2 times 1 over cosine squared y, right? That's still the same thing. And 1 over cosine squared y is just secant squared y. And that's what I would think is your best answer, since there's no fraction in it. Simpler. Oh boy. Who's next? Okay, fair enough. That's fine by me. Let's do this next section, and then we'll give you the rest of the class to work on the assignments. Okie dokie. Okay. So recall last chapter, we asked you to find the value for something like this, right? And when we didn't give you an interval, like in this problem, for sine, we know the interval that we're looking for is negative pi over 2 to positive pi over 2. So that's in quadrant 1 or quadrant 4. So if we went to the unit circle and we looked this up, we'd see that sine is positive in quadrant 1, and we would have retrieved the value pi over 6, right? But that's not the only place where sine is equal to 1/2, right? That also happens in quadrant 2, and then any values coterminal to those two locations, right? So that's what we're going to be worrying about here in this chapter. So consider this question that's almost identical. What's the difference between these two? Right, they're equivalent statements, but one is in inverse and one's not in inverse. Remember, though, when we constructed this inverse, one of the things that we had to do was restrict the domain on the parent function, or the original function, in order to make sure that our inverse wouldn't fail a vertical line test. Now, though, if I want the values for x that satisfy sine of 1/2, there's infinitely many of those, right? If you think about what the graph of sine looks like, you know, it goes like this. So like if 1/2 is here, there's infinitely many of those intersections, right? So let's talk about how we're going to find those intersections, okay? So if I want to solve for x, I'm going to go ahead. And I notice that 1/2 is a unit circle angle, right? So I can find where sine is equal to 1/2. So I get pi over 6, but I also get 5 pi over 6. So these are our answers. Whatever. Between 0 and 2 pi, right? Yes, Dan.
Erwin, I thought you told us that when you're finding the side of that it has been quadrant 4.
So if you're given this problem, yes. But here we're asked to solve for sine x equals 1/2. So we're accepting any value of x that causes sine to equal 1/2. So the sine inverse answers we're going to retrieve aren't just the things from quadrant 1 or 4, but anywhere on the unit circle that we can possibly get. Okay with that? And that's an important distinction, right? if we had extended this to say, what if we wanted all possible answers? How would I say that? Well, I'm going to get pi over 6, right? And then anything coterminal to it, where k could be any positive or negative whole number, right? That symbols for the integers are just the positive or negative whole numbers, like -3, -2, 0, 1, 2, 3. And similarly, we can do the same thing with 5 pi over 6. So what is this set of symbols really saying? It's pi over 6 and any angle to it. So like pi over 6 is here. So we're talking about this angle, and then that angle, etc., right? You guys get what I mean by coterminal? Just as a reminder what that meant. Is that okay? Let's try another, okay? Okay, so we're going to solve for cosine squared x is equal to 1 on the interval from 0 to 2 pi. Rewrite that. Remember that interval notation. This means the same thing as 0 less than or equal to x less than 2 pi. The bracket is the or equal to inequality. The parenthesis is the strict. Okay, so if we want to solve for x, what's the first thing that we should do to get the x by itself? Ben? Yes. Yes. So cosine squared, remember, means the same thing as like cosine of x squared. So we can get rid of the root, or the squared, by taking the square root of both sides. So remember, though, when we square both sides of an equation like this, what happens? Yeah, we get a plus or minus. Is everybody good with that? Okay. So I'm going to now split this into two separate equations. So I have cosine equals -1 and cosine x equals +1. We okay there? Okay. Then the next thing I would do is so if we go to our unit circle and look, I'm going to find my answers between 0 and 2 pi. Cosine of x is equal to -1. So the x coordinate of my unit circle needs to be -1. That happens at pi. And that's the only place. And we're equal to +1 at 0. and 2 pi. But if you look, really want just 0. Why not 2 pi? Because it's not an or equal to inequality on the 2 pi. So those are my 2 answers. Now I talked through how we looked at the unit circle. Let's look at the unit circle and point that out, just to make sure that we got it. If you have your unit circle, you could certainly be looking at it right now. Oh, look at, I have scribbly scrabblies all on my unit circle. So cosine equal to -1, there at pi, and equals +1 here at 0. And those are the only places where the x-coordinate is 1 or -1, right? So that's it. That one is done now. Is everybody okay there? Let's do another example. So let's do 3 times tangent squared x on the interval 0 to 2 pi. So again, if I just want to translate that into an inequality, that's not a big deal. What would I want to do to start with to solve 3 tan squared x equals 1? Divide by 3, okay? Everybody's okay there? Square root both sides. So remember both sides, it makes a plus or minus. And do you remember how to square root a fraction? So that just square root the top and square root the bottom. So the square root of 1 is just 1. But we don't like to leave a fraction with a square root in the denominator, right? So how did we? We rationalize the denominator. So that makes root 3 over 3. Oops, I don't know why I wrote the squared there. That shouldn't have been there. So x is going to equal, well, we should split that then, right? So we have tan x is equal to positive root 3 over 3, and tan x equals 3 over 3. Okay with this so far? Now I'm going to give you a little hint on these tangent ones. I'm going to be using the 1 over square root of 3 is a little bit easier to see where to find that on the unit circle. Because remember, tangent is y over x. And I know that 1 and square root 3 aren't exactly x and y coordinates on my unit, but if I divide them both by 2, they are. So if I go look at my unit circle, I'm looking for a place where the y coordinate is 1/2 and the x coordinate is square root 3 over 2. So I get the y coordinate is 1/2 and the x coordinate is square root 3 over 2. That happens at pi over 6. And it could also happen if they were both negative, right? So that would be at 7 pi over 6. Okay with that? And so, oops, I didn't mean to do that one. Oh my, a little bit scroll. So we have pi over 6 and 7. And then over here, we need to worry about if they could be negative, right? So I go back and I look at my unit circle. So I need a negative and a positive, so 11 pi over 6, and also 5 pi over 6. Okay with that? Dan? Yeah, so my y coordinate is going to be 1/2 and my x coordinate is going to be √3/2. So I'm just looking for anywhere in my unit circle where I have y is 1/2 and x is √3/2. So like here at pi over 6. Or they could both be negative, like over here at 7 pi over 6. Right?
So how do you like figure out that like your y has to go that?
Well, 1 over √3 is the same as √3/3, right? And if I do the same thing to the top and bottom of it, multiplication or division, it's still the same thing, right? So I thought about what kind of coordinates are in my unit circle. 1 and √3 aren't on there, but 1/2 and √3/2 are. So if I divide the top and bottom by 2, that gets me what I'm looking for on the unit circle. You know what I mean? So just like making a common denominator kind of thing, right? Where you can just, as long as you're doing the multiplication division to the top and bottom, it's okay. And it's pretty common when dealing with tangents. So you might have to do that. Okay. So far, the algebra has been relatively easy. Sometimes going to the unit circle and retrieving the values is not trivial. Let's look at another example here. What's different about this problem than the previous ones? We have more than one trig function being added or subtracted from each other. How will I need to attack this? Here's a little hint. Let's make a substitution and just pretend that A is equal to cosine. What would this become then? And this is something that we learned how to solve last year in our algebra class, right? So how would you want to solve something like this for A? Oh, come on, guys. This is like the most fundamental thing you did last year in your Algebra 3-4 class, is to solve this kind of a problem. What kind of problem is this? Okay, quadratic. So factoring would be one excellent possible way to solve this. Let's try to factor this one. If it's going to be a unit circle problem, it should be factorable. So let's try that. So to factor this, we need to find the two numbers that multiply to give me the leading term and add to give me the null term. Oops. Hey guys, I made a boo-boo. I made a boo-boo. That's supposed to be a -1 at the end. Okay. Wasn't very solvable before, was it? All right. So the two numbers we need are 2 and -1, right? What do we do with those two numbers once we have them? We replace that middle term with 1a, and then we make two groups. From the first group, we can take out a greatest common factor of 2a, leaving with a plus 1. From the second group, -1, leaving us with a plus 1. And then if I compare what's left, I see that both of these terms have an a plus 1. So if I factor that off, we're left with just 2a minus. And now we're factored. You guys remember doing that factoring last year? I expect you still remember how to do it. This is your refresher. So at this point, once we have it factored, we can apply the zero product property, set each of these factors equal to 0, and solve them independently. So I get a equals -1, and then a equals 1/2. But remember, are we solving for a? No, we're solving for x. So let's replace a with cosine of x. And then we'll apply our inverse, as I heard somebody whispering. And now I'll go to my unit circle and look up the place where x is equal to -1. Well, that happens only at pi. And at the place where x is equal to 1/2. Well, that happens at pi over 3 and 5 pi over 3. Is everybody okay with that? Okay. Let's look at the very tricky sine 2x is equal to 1/2. What would I want to do here first? Oh, we need an interval, huh? Sorry about that. So that gives us sine, or gives, I'm sorry, 2x is equal to sine inverse of 1/2. So I'll go to my unit circle now and look up the places where sine is equal to 1/2. So if I go to my unit circle and look that up, that is where the y coordinate is 1/2. So that's pi over 6, as well as 5 pi over 6. Everybody okay with that? Okay. And now you'd think, okay, we'll multiply both sides by 1/2 and we're done, right? Everybody agree? If we do that, we've missed a couple of solutions. To ensure that we haven't, let me explain to you what I want to do. I'm going to include this piece. So we're just going to say that answer and everything coterminal to it, right? Is everybody okay so far? So now, when I get the x by itself and multiply both sides by 1/2, I get pi over 12 plus pi k, or 12 plus pi k. So when k equals 0, I get x is equal to pi over 12. That's in the interval between 0 and 2 pi, right? When k is equal to 1, I get pi over 12 plus pi. That's 13 pi over 12. That's also between 0 and 2 pi. If I went to pi over, or if I picked k equals 2, that's pi over 12 plus 2 pi. That's going to be too big, right? That's bigger than 2 pi already because I have something greater than 0 plus 2 pi. So I'm going to get two answers from over here. The 13 pi over 12 was not totally obvious. Is everybody okay there? Similarly over here, when k equals 0, I get 5 pi over 12. And when k equals 1, I get 17 pi over 12. If I pick any big a, it's too big. If I pick any smaller values of k, it's too small. It's outside of that interval from 0 to 2 pi. So I really got 4 answers here instead of maybe the predicted 2. When will that happen? Instances where we have a coefficient attached to the x. Ben? Not necessarily, possibly. Depends on the interval that you're solving over also. So like if that interval was bigger, you could have had more, or if it was smaller, you could have had less. And if that number is like 1/3 or something, now all of a sudden it's not even predictable how many, if you're going to have 1 or 0, right? Yeah, because it doesn't work out evenly. So you have to be a little bit careful there. It's not a strict statement. Oftentimes, though, that is correct. Okay. But not always. So I don't want to overstate the power there of that statement. Okay. Okay, and just a million examples in this section, but that's okay. These are all good examples. All right, so let's say we have cosine squared 3x equals 1/2. We're going to have so many answers to this one. So first thing we would do is square root both sides, right? And we'll rationalize the denominator, make that really square root 2 over 2. We'll split that up into 2 equations. And we'll do the inverse. If I go to my unit circle, cosine is equal to positive root 2 over 2 at pi over 4, and anything coterminal to it, at 7 pi over 4 and anything coterminal to it. And then cosine inverse is negative root 2 over 2 at 3 pi over 4, anything coterminal to it, as well as 5 pi over 4 and anything coterminal to it. And then we'll divide both sides by 3. So I get x equals pi over 12 plus 2. I get 7 pi over 12 plus 2/3. I get 5 pi over 12 plus 2/3 pi k. And I get 3 pi over 12 plus 2/3 pi k. Okay. So when k equals 0, 7 pi over 12, 5 pi over 12, and 3 pi over 12. All of those are between 0 and 2 pi, so they're all acceptable. When k equals 1, 1/12 plus 2/3, I have to make a common denominator, which would be 12. So I multiply 2/3 by 4 over 4, making 8/12. So 8/12 plus 1/12 is 9/12, which reduces, we'll reduce later. Same thing here. So 7/12 plus 8/12 is 15/12. And then 5/12 plus 8/12 is 13/12. And then 3/12 plus 8/12 is 11/12. Keep going. Let's see if they're too big or too small. So now we're going to be adding 4 pi over 3. Again, we'll make a common denominator. 4 pi over 3. Multiply the top and bottom by 4 gives me 16 pi over 12, or 16 pi 12ths. So 1/12 plus 16/12 is 7/12. That's still smaller than 2 pi, so that's an acceptable answer. 15/12 plus 16/12 is 31/12. That's too big. We'll cross that out. 13/12 plus 16/12 is 29/12. That's too big, right? 2 pi is 24/12. And then 11/12 plus 16/12 is 27/12. That's too big. Oh my goodness, I'm adding the wrong things, aren't I? Gosh dang it. Sorry, guys. I'm supposed to be adding this 16 plus these guys. Great googly moogly, Mr. Kulik. I can't believe you screwed that up so badly. Neither can I. I really sincerely apologize. This is hard enough without your teacher making... But he did it, and he apologized. He didn't mean to do it. I added, instead of adding 16/12 to this one, I added to this one. Right? Because we're doing this plus that. So I just, okay. All right. All of those are still less than 24/12, right? Okay. K equals 3. So now we're going to add 24/12 would be the next one, right? Which is already going to be too big, right? So all of these are no. So those are my answers. I would just need to reduce when appropriate. So like this one is 3 pi over 4. This one is 5 pi over 4. This one can't reduce. Neither can that one. Neither can this one. Neither can this one. This one can. 7 pi over 4, and that one can't. Dan.
So like when you're doing like for example the table two, like the row for that one,
Mm-hmm.
it's doing it. So,
Well, you can just add 2/3 pi to get to the next one, and you're just doing the same thing each time. Yeah. Yep. Is that okay? That's maybe the easier way of thinking about it. After I got halfway through, I'm like, oh, I'm stupid. Is that okay? All right. Next example, and I think we'll probably pause here after this example. And we'll just come back and get the rest of these another time and give you a chance to work on. How's that sound? I know, right? Amazing guy. Okay, so we have tan 2x times sine squared 1/2 x equals tan 2x. And we're solving that on the interval from 0 to 2 pi. Who wants to divide both sides by tan 2x? That's a bad idea. So remember, like when you're solving, like quadratics or something, and you have this, you can't divide both sides by x because you lose solutions, right? You'd had to have moved this to the other. You guys remember kind of doing things like that last year? Same idea here. So the first thing we would do, that tan 2x to both. So that we can factor it out. And a zero product price equal to 0 and solve. So tangent is equal to 0 when the y coordinate is equal to 0. So that happens at 0, and it also happens again at pi. Oops. Now, and then would have pi, right? I'm going to consolidate this together. So instead of saying each of the, I'm just going to say 0 plus pi k. Because notice that I'm getting a solution instead of every 2 pi, I'm getting it every 1 pi. That happens for tangent. Why would that happen that way for tangent? And not sine or cosine? What's the fundamental period for tangent? Pi. What's the fundamental period for sine or cosine? 2 pi. Remember when we graphed them? That's the reason. And so now if I divide both sides by 2, I get 0 plus pi over 2k. And we'll come back and do the iterate out how many we need here in a moment. Dan. This part. So I go to the unit circle, and the place where tangent is equal to 0 is when the y coordinate is 0. That happens at 0 degrees when it's right here on the x-axis. And also here at pi, where it's 0. And then again at 2 pi, and then again at 3 pi, and 4 pi, and 5 pi, and 6 pi. So it's every pi units it's hitting another one of these points that we care about, right? So I just consolidated down that into 0 plus pi over k, or pi plus k. If we do the other one now, we'll add 1 to both sides. We'll square root both sides. We have to split that up into 2 pieces then. Oops. And then do our inverses. If I go to my unit circle, sine is equal to 1 when the y-coordinate is 1. So that happens at pi over 2 only. And then when sine is negative 1 happens at 3 pi over 2 only. Well, and everything coterminal to it, but then we multiply both sides by 2. So when k equals 0, this one gives me 0. This one gives me 3 pi, but that's too big already, right? Because our interval is from 0 to 2 pi. When k equals a half, I get pi over 2. Then I get 5 pi. That's too big. And this one I don't even have to compute because it was already too big on the first one, right? It's just going to... On the next one, I get pi. I don't have to worry about these ones. Already too big. When k equals 3, I get 3 pi over 2. I don't have to worry about these ones. And when k equals 4, I get 2 pi, which is technically too big. So these are my answers that I found. I don't have to list pi twice, even once. So those are my 4 solutions. I'm going to make a note here of where we stopped, and we'll pick up with some more examples next time. As for the assignments, you really, if we've done enough to where you can do all of 50, those all have 4 parts to them, A, B, C, and D, but there's not much you have to do once you've got part A to get parts B, C, and D. But don't feel like you need to finish it all in one night because we'll do more examples on this topic. And I would also say you should start looking at worksheet 2, where we have some more simplifying trig identities practice on that one. Yes, Delaney?
What are the problems for worksheets when you get done?
For the worksheets,
And the problems.
I don't have it planned out ahead. I just do it like class by class, depending on what we get through.
Okay.
But I do promise you that by Sunday evening, or by Friday afternoon, I should say, if you go to Power School and you look at the calendar, on Sunday it'll list everything that I'm looking for on my checks.
Okay.
So I have been trying to make sure I do a good job of that. If Power School wants to load here, I'll show you exactly what I mean.
Okay.
But it looks like it's going to be stubborn here for whatever reason.